Hello again. This is a solution to the second part of problem 8 from my spring 2020 final exam. Here we are given another sequence. In fact, it's sort of built up out of two sequences, and we want to know whether or not it converges. And if it does converge, we want to know what it converges to. So since we have this minus in between these two pieces, it's probably going to be very handy to consider two other sequences, namely, let's define C sub n equal to, well, let's look at this, 3n to the fifth minus 4 over, oh my goodness, all this other stuff, 2n to the fifth minus 3n cubed plus n plus 3. And then another sequence, dn, that's going to be sine of n over n. And the reason why it'll be handy to look at these different sequences is we know that if I subtract the sequence C and D, all right, that this is equal to the sequence B. Furthermore, I know that if C and D converge to K and L, respectively, then C minus D, which of course is equal to our B, will converge to K minus L. So if I want to show that B converges, it's enough to show that these two individual pieces converge. All right, so let's look at those separately. So first, let's look at the C's, right? So our C sequence, well, let's see what happens as I take the limit as n goes to infinity of this 3n to the fifth minus 4 over, well, all this stuff on the bottom, 2n to the fifth minus 3n cubed plus n plus 3. Now what our intuition should tell us is that the limit is 3/2. We look at the highest degree powers of n. They're both n to the fifth. We ignore everything else. We cancel the n to the fifths and we get 3/2. Okay, that's what our intuition should be. Okay, we can show this directly by multiplying the top and the bottom by 1 over n to the fifth. So now we'll have the limit as n goes to infinity of, okay, on top we have 3 minus 4 over n to the fifth, and on the bottom we'll have 2 minus 3 over n squared plus 1 over n to the fourth plus 3 over n to the fifth. All right, and now each one of these each one of these individual pieces is going to converge to something. Well, the 3 and the 2, they are what they are. And the rest of these, as n goes to infinity, all converge to 0. And so this limit will be 3 over 2. All right, so this implies that the sequence C converges to 3/2. Okay, how about this sequence D? So D, now we're trying to understand what happens to sine of n over n as n goes to infinity. And this is a little trickier because while this n on the bottom is blowing up, this sign is oscillating back and forth between -1 and 1, which maybe concerns us a little bit. However, the squeeze theorem is going to help us out here. We know that the sine function lies in between -1 and 1. If we then divide by n, and n, of course, is going to be positive, right, as n was going to infinity, then none of these inequalities change. But we know that as n goes to infinity, -1 over n converges to 0, and 1 over n converges to 0. And so by the squeeze theorem, for sequences, which we've proved in another video, the middle piece also must converge to 0. So we conclude that limit is 0, i.e. the sequence D converges to 0. So it follows, by what we were saying up above, that this original sequence B is going to converge to 3/2 minus 0, or 3/2. Not too bad. Not too bad at all.